So 2004b, hydrogen peroxide decomposes according to the equation above. So we had to start with hydrogen peroxide. We finished with 2 moles of water and oxygen. Part A says an aqueous solution of H2O2 that is 6% hydrogen peroxide by mass has a density of 1.03 grams per milliliter. Calculate each of the following. So number 1, the original number of moles of hydrogen peroxide in a 125 milliliter sample at of the 6% hydrogen peroxide.
Boy, that is a fun question. Have we had something like this before?
Yes, we have.
When?
No. You should know how to do it. Good job.
So no,
Abe.
I don't believe we've ever had a question like this before. Okay. However, you're given some important information. You're given a density and you're given a volume. Now, back when we talked about molarity, everybody remember molarity? What's the unit for molarity? Moles over liters. And if you knew both the volume and the molarity, what should you start with? Volume, because we want to get rid of, in this case, the volume because we're going to need grams for this. So with this, so we're going to start with the volume, so 125 milliliters. And since in this case we know the density, which has mass and volume, we want to get rid of the volume, then we'll plug in our density here. So what happens to the volume? Goes away. And now it turns into somewhat of an easy question. Really? I don't think so. So now the next component is...
What the heck does that mean?
You multiply it times on the amount of grams times 0.06, and that's how many grams of the actual H2O2 you have.
So why are you saying that? Why 0.06?
6% would be 0.06.
So what you're telling me is that this 6%, that in the hydrogen peroxide solution, only 6 parts out of 100 is hydrogen peroxide.
Yes.
Okay, good.
So you can do that. You can pretend that you have a 100-gram sample, because again, we're trying to get rid of grams here. So if you put 100 grams down here and 6 on top, is that like what Ryan just said? Works out wonderful. So if we stop right here, now we have actually our number of grams of our hydrogen peroxide in that 125 milliliter solution. But is that what the question's asking? No, we need moles. So we need to go one more step. So again, we're going to put 1 mole on top and H2O2, so whatever the molar mass of that is. Hang on here, what? Like flying. One more time.
34.016.
See this line here? I want to make sure it stays above. So it's actually, that's where I'm at right now, from here to here. So this is the node. This area right here, that's garbage. Can't draw in there. It won't show up. So we now have, what's our answer for that? What is it? 0.227? Does everybody agree with that? Yeah. Okay. So that's the first part. Oh, moles, you're right. Good call. Okay. So the hard part of this, actually there's 2 components here that might throw you off. The first one being the density incorporated into that, and then the second one being 6%. So remember, whenever you're given percentages, think of 100 grams, okay, and then how many grams of that. So it goes like back to empirical formulas and percent compositions there. All right, so that was I. So double I. All right, double I. The number of moles of oxygen are produced when all of the hydrogen peroxide decomposes. So a little stoichiometry. So we're coming back to here. So we know how many moles, and this again is of our hydrogen.
So how would I?
There's that and start and then go to mole ratio.
So the ratio hydrogen peroxide is 2 to 1.
Slide this here. All right. So we'll start with what we finished with. So we have 0.227 moles of hydrogen peroxide. ratio, moles of hydrogen peroxide to moles of oxygen. Again, for those viewing at home, we have 1 oxygen for every 2 hydrogen peroxides. Okay. And then whatever half of that is. 0.11. And that is a...
Now, that has nothing to do with kinetics. But again, whenever we're looking at these types of questions, we're still building on what we've been talking out throughout the year. So the expectation is, hey, I learned that back in September. I still want to be able to do that. Yay.
B says the graphs below show results from a study of the decomposition of hydrogen peroxide. So again, whenever we're looking at these graphs, we must look at the y-axis. So you have to focus on what we see here. But before we go to part I and write down the rate law, I do want us to look at, this is day 107, page 202, so if you want to turn there real quick. Okay. So these graphs, this is, again, on the AP exam, on the test, on the quiz, last quiz. You need to know, whenever you see the slope, what's going on and what order it is. And this is actually going to help you for your lab. So here we have our 3 scenarios here. And we have concentration versus time. And I gave 0 order, 1st order, 2nd order. Okay. And we should be able to recognize and make sure that this is actually high enough here. Okay, so looking at those, what would we expect our graphs to look something like when we look at these? In other words, looking at the 0 order first, how should I look at?
What should I expect? Negative slope. Good.
So in other words, when I do this, it's going to look like that. Okay. So it's always going to be a negative slope if it's a 0 order, because again, when we talk about whenever we talk about 0 order, it doesn't matter how much we have, just as long as we have it, that the reaction is going to proceed. And then for 1st order, hopefully this is, oops, let's not do that. Let's go back there. So it's going to do that. And 2nd order would be a little closer, something along those lines. Again, don't erase. It's still going to be a curve. You're not going to know if I went ahead and had this and just, let's get rid of this guy here. Oops, sorry. Too soon to do that. Let's try again. There. So technically we could look at those curves and not know what the order is. So 1st order, 2nd order, we have no idea. 0 order, we absolutely do know that that's going to be a 0 order with a negative slope. So again, when looking at these graphs, we know that it cannot be what? If looking at these 2 graphs here, it cannot be 0 order. Good, okay. Sometimes the most obvious answer. All right, so looking at B, so now we have natural log of A and the natural log of A versus time for 1st and 2nd order. What would you expect on the 1st order? A negative slope, good. And what would you expect for 2nd order? And again, some of you who have done the lab or actually typed it in on your graph, what did it look like? Went like that. Okay, so it's still a curve. It wasn't positive, because hopefully some of you had the 2nd order, and when you looked at it, you're like, hey, that still is kind of curvy. So if I have a natural log of A versus time, and I'm looking at that information, I can tell that it's definitely not what? 1st order or 0. Well, we don't really know what the 0.
What did you guys have when you did 0 order? Actually, we do know. What did you see? Come on, who had a 0 order? Anybody have a 0 order? Yeah. So would it look like natural log of A?
It's still.
Did it do that? Yeah.
Did it do that? Wouldn't be a bad idea to have that. Especially if you haven't finished your lab yet and you're like, hey, that looks kind of weird. Is that something I should expect? Yeah, that is something. Okay? And that's, sorry, again, this is zero order, not second. Second would be the regular, whatever, curve down. Okay. All right, and then the last one here. So if I'm looking at this first order, let me move that up a little more, get it in the viewable area. Okay. Those of you who have a first order, how did your 1 over A look?
So an acceleration? Yes? Well, look. Whoever has, take a look.
Because it's just the inverse of the first order.
Yeah.
So it should be a curve that goes in that direction. I call it acceleration, but I know it's not called that. And then for this one, it is positive slope. So there you have three slopes. So the inverse of the concentration over time represents for a second order. And then for the negative slope of natural log of A over time, that represents for a first order. And then concentration versus time, negative slope, represents for a 0. Those are the three you absolutely must know. The other ones are nice to know. Yeah, right.
Could I figure them all out from natural log? Because they're very different things.
Sure.
But hopefully, if you're given the graphs, you better be able to go, make your decisions off of that. Because you're not going to be graphing during the test, during the AP exam. That's when we have all this luxury time in class. Questions on the graphs? All right, so back to here. So looking at the graphs here, so it gets pretty easy now, so we just talked about it. And I know it's a dumb question, but do these two graphs represent the same data?
Yes.
Yes. That's really important to know that they represent the same data.
And we can do a lot of things with these graphs. So part I says write the rate law for the reaction and then justify your answer. So what would you say the rate law? Yeah, Ryan.
Rate equals K times the concentration of hydrogen peroxide.
So
hydrogen peroxide. And again, it's totally optional. If you want to leave it as is or put the 1, doesn't matter. Now, the justification, because again, it says to justify your answer. So there's two parts in this. So the first one is the actual rate law. The second one, what would a good justification be?
The slope of the natural log of the concentration of hydrogen peroxide is negative.
good.
So we are focusing on this graph here. Okay. And we have to talk about that A, when we have the concentration, the natural log of the concentration versus time yields a negative slope. That's all you need to put, too. You don't have to get into how fancy your answer needs to be. Just answer the question. Negative slope, put what your y-axis is versus time.
You don't need to say it's linear.
No, because slope is linear.
Double I says determine the half-life. Determine the half-life. How are we going to determine the half-life? We have what? Say it again.
Okay, so what graph are we going to use, the left or the right? See, Hannah pointing this way. So, how many want to use this graph here? How many want to use the graph on the right? Go ahead, Abe.
Oh, you said how many you want to use?
Want to use this one for figuring half-life?
Yeah,
Yeah?
I'd like to.
Well, let's come back to what the majority liked. All right, so
half-life deals with how much remains. I'm sorry, the amount of time when you have half of the original material remaining. So we started off with a 1 molar. So what is half of that?
0.5. So I'm going to try to be really close here.
So 0.5 is there. Okay, so that's our first point. Then the second one is to actually find out where that intersects in the time. So I need to move it over a little bit here. Hope I don't move the picture. Of course, I'm moving the picture. Picture. Come on, go this way. I change the arrow. I cannot. Awesome. Love it. All right. So we're going to pretend that this point right here is actually there. Now, I'm going to tell you, this question was on an 8.5 by 11 sheet of paper. This is blown up. Okay, so it's a little easier to see. But approximately, what is that time right there?
700 minutes.
6 approximately.
700. It's totally 700. 700 minutes. That's a good guess. If you divide
725.
730.
you know what the graders are going to give you credit for?
600.
Between 600 and 750. So, the key here is whatever you choose, okay, make it within a reasonable range because, again, we don't have a table of data over here. We don't have a bunch of numbers that we could actually use to make this an easier process. They want you to analyze the graph and be able to determine, number one, which graph am I going to use? Am I going to use the one on the left or am I going to use the one on the right? Well, the one on the right is a lot harder to find points. You absolutely could. You could find the slope of this thing and be able to determine half-life from that. But it's a lot harder because really there's only 2 points and we don't want to use the 0 point. There's one that kind of intersects. But here, this is what they're expecting you to look at, the graph on the left. So what do we want to say as a class?
725.
700.
I'll go 700.
725. We'll go with Baylor.
Right.
So we're going to say that the half-life is 725, which, again, whatever value you choose, it has to be reasonable. In other words, if you looked at the graph and you said, I'm feeling 500. No, 500 is that line right here, okay? So that's 400, you're right. Thank you. Again, being able to read a graph is pretty important. So it's not close enough. It's definitely closer to the 800 than the other side. So make it, quote unquote, reasonable. So if we say 725, and that was in minutes, okay? And does it ask for us to justify? No. So don't waste time trying to explain. Okay. Triple I. Here's the fun thing. Okay. Calculate the value for the rate constant K. Include the appropriate units in your answer. How?
Wait, 500.
Good. Okay, let's go back. What is the order? First. Go ahead, Hannah.
Okay, 2 things. First, could you just do the slope of the second graph and then get it, since you do have 2 points?
Where's your 2 points? I can definitely see this one.
Okay.
Where's another one?
Top left.
You mean here at 0?
No.
Yeah.
No, we don't want to use that.
And I'm going to give you a hint. The graders are wanting you to use what you just found. Okay? So since we just determined the time here, can't we use the equation? So
we want to use the equation.
So we want to use the equation. And again, this is part of the game that College Board plays. They're giving you a question. They want an answer. They want you to use that in the near future. You could use that too. So again, on the equation sheet, you're given that, which is, what is it, 0.0? Now, is it negative above? Okay. And then, what do we put here, K? Okay. So, either way, but be sure to show that. Just don't automatically dance into the answer. So 0.693, and we said it was 725 minutes. Somebody calculate that. 9.564. And again, our unit, let's make sure we can see it. What is it?
Molarity of
1/2.
It's over time.
Over a second.
It's not molarity. Remember, what is the reaction order? First. So 1 minus 1 is, so there's no molarity. It's just time, and time is minutes. Time is minutes.
So that is our K. Okay. And what happens when we take the natural log of any unit?
Goes away.
Okay. So don't include that in there. All right. Where are we at? 4. Determine the hydrogen peroxide after 2,000 minutes have elapsed from the time the reaction began. So we're actually looking, and they're not looking for you to find that on the chart or for you to come over here. They actually want to they want you to calculate it, so to speak. It is, you're right. Okay. So we have our equation, and I'm going to modify it here. So we're looking for that concentration. And what did we start at?
1. So this was one of the times that we started with 1, which is nice.
And we know our constant, and we know our time. Move that a little more. So now our equation looks like this. We have a T. And it is, oh wait, no, I want to leave it. So negative KT, 1.56. You guys are getting all this in?
Wait, why are we using 1?
Because it started with a molarity of 1, so that's our initial concentration.
What's that T?
We're looking for this. This is our question mark.
Oh, yeah.
We're looking for that.
It's a negative.
And the time was 2,000? Okay. Sorry, 2,000 minutes. My bad. I know. So the minutes cancel. And what'd you guys get for a value here?
Oh, I already took the E of it.
Okay, well, I'm sorry. We need a number here first.
Negative 1.912.
Negative 9.12?
Negative 1.912.
And it's in your calculator, right? All right, so to get what?
9.12.
No. All right, so now we have our natural log, question mark, and we need to get rid of that. So we need to do what to it?
Take E.
Put E to the other.
E to both sides, right?
So 1.912.
0.148.
What happened to negative K?
Okay, so let's say I didn't do that original first equation, and I might have just taken E and then parentheses up the top, the K and the T. Would that be okay?
If you showed it.
I did.
Yeah, okay.
Yeah, okay. I'm sorry, what'd you ask, Ryan?
Nothing. Nothing that needs answered or brought back up.
So now we have, and what was the value of this?
0.148.
Is there a unit on that, Lauren?
No.
Yes, ma'am.
Okay.
Because again, what does the brackets represent?
Concentration.
Right, molarity. So make sure you put the value on it.
Now, let's take a peek for reason. Make sure it's reasonable. 0.148. Does that seem reasonable? So through this point here, yeah, not too shabby. Deal with that. Pretty good for government work. Questions on 2004B?
Yes.
So it could be anything from past that on this test.
Yes. Isn't that fun? Peyton looks like that is what we want. We want, oh my gosh, throw in stoichiometry, thermo's almost given.
Really?
Yeah.
Along with this unit?
Yeah.
Let's look at 1996. 1996. So these are, I call this an easier question. I hope you do find that easier. All right, so we have the reaction of nitrogen monoxide and hydrogen is believed to occur in the following three-step process. So we go fast, slow, fast. Okay, so again, we're on 1996. And the first part says, write a balanced equation for the overall reaction. So who can we cancel out?
N2O.
N2O2.
N2O. Okay. And so 2NO plus 2H2 yields 1 nitrogen and 2 waters. Is that right? Okay. Now, yes.
How would you know what air is used? Because the first one is a numbers.
Equilibrium is okay. Is that what you're asking?
Yeah.
Yeah, it's all right. Doesn't change anything. So the rules still apply when we get to the rate law, whether it's equilibrium or not.
Now, here's one thing that especially when I was grading the quizzes, you guys wrote down the overall balanced equation, but you didn't check to make sure that you actually had the same number of atoms on both sides. So use that. That's a skill that you have to check to make sure that, okay, yeah, 2 nitrogens, 2 nitrogens, 2 oxygen, 2 oxygen, 4 hydrogen, 4 hydrogen. Good. Okay. There were some God moments, like poof, there's a carbon monoxide atom. There's no carbon on the right. Okay.
How come you don't have to do double arrows?
It's just the overall. So it's not the final answer on that. So, yeah. If you did, I don't think they'd count it wrong. But primarily what we are looking for.
So identify the intermediates and then explain your reasoning. So who are my intermediates?
Or your intermediates.
N2O2.
Okay, so.
2 and N2O. All right. So justify. Or explain. Sorry, explain.
They were products. Yeah.
Say it again. Okay. So, by definition, intermediates are something that are produced and later used as a reactant. That is a great explanation. The graders will just salivate on that.
We're talking not like the immediate following.
Doesn't have to.
Okay,
Yeah.
so it could jump.
Look at this.
Yep.
a reaction.
So it could come back later on. Now,
Now the question was, doesn't have to follow in the next step. It could come back in a step or two later. So, again, these are proposed mechanisms. Doesn't mean that we're actually going in the lab, stopping the reaction, checking out who's there, and then moving on. All right. C says, from the mechanism represented above, a student correctly deduces that the rate law for the reaction is given here. Okay. So the rate law, include the rate as well. So that means that there's the NO has a second order, the hydrogen is first order. The student then concludes, well, let's first of all, is that the correct rate law?
Yeah.
Yeah. No. Yes.
how many NOs?
Well, first of all, here's the slow step. So who are my reactants?
It's
Okay? So it wouldn't be H2 squared, or to the second power, because the second hydrogen follows after the slow step. So include all the reactants up to including the slow step minus the intermediates.
You don't have to check the student because it says they correctly.
I know, but it's nice to make sure.
Because you never know if the student is correct. Because here it says, okay, then the student concludes that the reaction is third order. So let's answer that. Is the reaction third order?
Yes.
No.
It's no such
Yes.
thing. Yes.
Overall
It's not the
overall
reactant. It's a reaction.
That is a true
So the
fact.
key here is reaction.
So the key here is reaction. So the answer is yes, because reactant can only be 0, 1, or 2. Reaction can be anything, as long as it's a whole number in AP. All right, so we'll come back to that. 2 says the mechanism involves the simultaneous collision of 2 NO molecules and a hydrogen. So again, what's happening is that the NO, the 2 NOs are coming together, and then the hydrogen's coming in, and they all collide at the same time and make our...
Isn't that one's like super rare?
I'd say
Like,
no, because the hydrogen collides later. It's not simultaneous.
And, more importantly, what is the hydrogen colliding with? Yeah, so that's your explanation.
The answer is wrong. It can't be that. There's no way that, and I like what Hannah was saying, that it's very rare, number one, for 2 things to collide correctly, let alone 3 collide correctly. But your equation even shows that you have to make the N2O2 before you go and react the hydrogen. So that's a great explanation. The answer is no, you cannot do that, or the student is wrong, and that the 2 NOs have to collide correctly to form N2O2 before the hydrogen can get involved. Yeah.
So it asks, are conclusions 1 and 2 correct? Will you need 2 separate answers?
Yes, so you'll talk about 1 being correct, and that the reaction order is just the sum of the reactant orders, done. And then 2 is no, what we just talked about.
Is there a name for like how many collisions happen?
No, we don't get into like secondary, tertiary, and no, not for a collision, yeah.
All right, and then the last thing we'll talk about here. Part D says explain, or is everybody good with C? Everybody get that? Okay, so D, explain why an increase in temperature increases the rate constant K.
Is there more energy and that makes them collide more, which gives greater chance that they'll come together.
Okay. Does equilibrium have anything to do with this? No, because the whole reaction is not equilibrium. So what Rashad said is good. We're talking about, these are typically gas particles, and so if you increase the if you increase the temperature, these things are moving more. You increase the likelihood that they're going to collide if they're moving more quickly. Okay? So don't get into Le Chatelier. This is not a Le Chatelier situation here. If it was only the first step, then what else would we need to know about this reaction? If it's endo or exo, good. And we are not given any of that information. So don't fish in that pond. Don't go and say, oh, no, it's going to slow down because it's endothermic or it's exothermic. We don't know. Don't make stuff up. All right, so only use what you know. Yeah, Maggie. Don't. It would, and remember that whenever you're explaining things, if you put in incorrect information, it actually invalidates the question. So don't make stuff up.
So, questions? Feel good? Okay. Tomorrow's quiz, NIMSY style.
Oh.
Is it time?
Yeah. So I'll pass back the quizzes before, let you take a look at them, and then we'll take it.
So it's like the one question 18-minute problem.
Yep.
Do we have more than 18 minutes?
Oh, we'll see. We'll see.
Yeah, no, we're gonna have 10 minutes.
Oh,
now.
that's
see.
really
With
cool.
multiple
10
parts.
minutes? Yeah, that's good. That's a good
How about you just flash your
Because
press
you
screen
didn't
real
have
quick? Okay, is there any way I could pick that up by the end of the day, or do you want me to get it tomorrow? I was just gonna practice tonight, so we only have one practice.
I might have it done by the end of the day.
If not,
Because we're going over limiting reactants here.
oh yeah, if not, it's totally cool. I'll just do them anyway. I still have to get to them, because that's what I was gonna ask, because I didn't know.
Day 1 of 7, like, video tonight.
Because it tells you what you're
I don't know. I just saw the answer stuff, but I didn't see it.
Yeah, why didn't you go so?
First of all, and it's true.
Why did I not?
I would be just surprised.
Yeah, because you were blazing.
Yeah,
Oh, that's 1/7.
So does this have video too, or just
Stay.
I don't know. Yeah, I don't know. I would assume that the whole thing, all 107, if that's
What?
video.
Yeah.
But,
I got a
yeah,
12.
experiment.
25.
I just didn't know that that stuff would be on there too, so.
You know, 29.
Always good time.
Are there any NIMSY practice questions though, that, other than these, like, you know how you
Yeah,
said those?
didn't I in Google Classroom?
I'll look,
Are you gonna
yes.
sell that in the reggae competition?
Let me look. I thought I did.
That's
but I'm
his
not sure.
side. He's gonna bribe the judges.
I mean, it's
business.
for it,
You gotta,
but
you gotta sell.
that's why I said the NH, because they talk about that as they need something, like the rarity of replay at one time.
Hey, look at that.
That's because we chose to play a low read. You don't play a low read and went outside with an everboard.
Low reads are fun to you, or they're fun?
Yeah, but maybe these parts, right? Everybody else has.
Loads are a lot harder.
Friday.
What are we doing Friday?
Loads are a lot harder.
Yeah, but like, you don't get the notes.
So much. That's so much.
Well, honestly, like, there's this one part where I play 2 low games in a row.
There's a part where Olivia has to play
So much shade. Oh my god. I couldn't even.
Doesn't that not exist? Oh, B flat. I play low B flat. Like everything else.
Here, I'm good.
Third to the last.
Try it.
Yeah.
So it just goes all.
Have a good day, guys.
Sorry, Mr. Greg.
You're fine. I didn't know.
Criminology.
But sure, have a great day. Thank you.
Criminology.
That's fine. Thank you.
I can do it.
I will try to have a day.
Thanks, Mr.